Hi, everybody. Welcome to today's Power Corner. I'm your host, Aalyia Shaukat, Editor-in-Chief of Power Electronics News. Today, we have the privilege of speaking with Carl Schlachte, CEO of Ventiva. Hi, Carl. It's good to have you here. How are you doing
Great to
today?
be here, Aaliyah. Good to see you.
Well, thank you for joining me. I know I did a little bit of research about Ventiva. It's a fascinating company,
Mhm.
and I understand it centers on its solid state cooling or ionic cooling technology, which apparently is based on the principles of electrohydrodynamic or EHD flow. Can you describe a little bit about the underlying physics of EHD in more detail?
Sure, absolutely I can, and big props for going after electrohydrodynamic flow the way you did. Very,
Thank
very
you.
few people do it. So
That was a mouthful.
exactly it is. That's why we never use it in any of our PR, that's for sure. Actually, to be fair, that
Yeah.
principle, EHD, is the shorthand that everybody uses for it. That principle's been around a long time. I think
Yeah.
Faraday might have been the first one that
Okay.
that
Yeah.
recognized this thing that was happening around in the presence of voltage.
Mhm.
And in our case, we use this, right? What we do is we energize a wire. We call that the emitter. That emitter is a standard. I'll call it a straight wire. So there's nothing. The materials are special, but there's nothing special about the wire itself.
Gotcha.
As
Okay.
you um, as you energize that wire, voltage and current, a plasma forms around that wire. And that plasma is an energetic field. It's actually one of the states of matter, right? But so plasma forms around the emitter. That's an energetic field, and the air around it, made up of oxygen and nitrogen, has ions associated with it. What happens in the presence of that field is the ions get stripped away. Some of them do, not all of them, but the ones that are in proximity to the emitter. As those ions get stripped away, if you remember your high school physics, ions have a positive charge.
Yeah.
They are drawn from the emitter. Those ions are drawn towards a negative, what we call collector, a plate
Yeah.
that's some distance away from it. And as those ions cross the gap between the emitter and the collector, they strike other air molecules that are sitting in between. And just like billiard balls, they transfer their momentum and
Mhm.
you get air movement. If you can sustain that reaction, that cascade effect gives you air movement. So like I said, the principle itself has been known for a very, very long time. What nobody's really been able to figure out how to do is turn it into something that can sit in the palm of your hand and can cool a laptop or a server. And so that's what we do.
And that's what you guys have done. And I know
That's
that you're
correct.
already
Yeah.
in laptops. Can you explain a little bit about that commercialization, the background of how Ventiva broke into the data center market from consumer electronics like background like
Sure.
laptops?
Sure. I guess the easiest way to explain it is if you think about traditional air movement, it really does literally center around a rotating mass, a fan, right? So
Yeah.
what's happening? In a fan, we are energizing a motor. The motor is attached to blades. The blades spin on that motor and they push the air, right? But at the end of that process, what you have is a geometry that is based on a circle.
Yeah.
And you know that, I mean, you intrinsically know this. I think we actually have this thing we call it at Ventiva when we're working with a lot of thermal engineers, we call it fan blindness. They've seen a fan so much that they can't unsee air movement associated with a fan.
Yeah.
It's fascinating, right?
Yeah.
That's a geometry thing, though. The thing I want to point out to you is that is fundamental at its heart. It's a circular piece of literal machinery. We're replacing this with something that looks essentially like a Lego. It's a square, it's a rectangular device about 4 or 5 millimeters high by as much as 60 millimeters long, and and you can combine these in multiple ways to get air movement. Well, pardon the pun, that's a long-winded way of saying that what we're actually doing is taking the geometry of a circle out of these things, which takes
Mhm.
up a lot of XY surface area, and replacing it with
Yeah.
something that's fundamentally smaller. What that means is you can fit our stuff, you can get air movement from our stuff to fit in other places that you couldn't otherwise get air movement. You're depending on some rotating mass far away to push enough air to get to this thing. Okay.
Yeah.
So in don't want to suggest to any of your listeners that this thing that we've got is somehow going to replace the cooler that you've got sitting on top of your NVIDIA Blackwell.
The liquid directed chip
Yeah,
cooling and
right. We're not, that's not what we do, right? What we
yeah.
do is in particularly in a server is our devices sit at the back of the server where all the hot air is now accumulating, and we fit in spaces where air movement cannot get to. So in between DIMMs or a voltage regulator module or NIC cards sitting at the back generally we call them thermal orphans, right? These are products that get hot on their own, and whether they stay cool, if they don't stay cool, you end up with a server that throttles on the back of you gotta have a $10,000 rack throttling on the back of a $500 NIC card because the NIC card is overheating. So if you get a little bit of air movement back there, you can solve a lot of problems. And in fact, that's what we do. So
That is fascinating. I was wondering how did anything change to jump from the thin laptop to a 1U or 2U server in terms of architectural cooling?
sure. Two things. Well,
Yeah.
first of all, I should say the fundamental part of our architecture, no. So now I don't, I hope none of your listeners are actually doing data center solutions, because we charge more for the same product when we put it in the data center. I really shouldn't admit that out loud, but it's the same thing. What we do, what we do is because as I said, they're Legos, right?
Yeah.
So you can take our devices and actually stack
Mhm.
one or two or three on top of each other and get 3 times the performance.
Okay.
And so ganging them up or turning them into,
Mhm.
strange shapes to get at airflow in a corner or something like that, that's where our bread and butter is. We
I
allow
see.
you to get access to that way. But it's the same fundamental thing.
And then that's why you were specifying, in between DIMMs and near
Correct.
VRMs, and
Yep. DIMM's a
I
great
got it.
example. You cannot get
Yeah.
a lot of airflow through DIMMs from a remote fan that's sitting at the front of the rack. It's very difficult.
Gotcha. And this was actually in the press release, the CES press release,
Mhm.
that only 25% of airflow reaches the compute components, while 75% is used to remove heat. And this is, you know, and so this is what you mean by what it means to direct cooling at specific components rather than relying on bulk airflow, which is kind of what we're seeing today.
Right, you have it exactly right. So,
Okay.
good job doing your homework. Well, look,
I got
it
these
is
index cards.
right.
It helps.
But the thing that no, the reason I say that is that this is kind of we're a little bit in the thermal weeds when we talk a lot about this stuff. People just assume, I think in general, the folks that don't understand how bad the heat problem is in a server do
Mhm.
just assume that somehow massive bulk airflow that's sitting at the front of the server. I mean, just so we're clear, 15% of the power budget for a 2U server is going to drive the fans. Like that's the only thing it does. You're spending money on blowing air. And that sits at the front of the machine, right? So what
Yeah.
happens? The front of the machine is where all the high value components are. And the back of the machine, where those thermal orphans we're talking about, get any airflow that is left over as it gets to the back of the machine. And that is hot by the time it gets there, right? And so when you talk about, the effect of that bulk air movement at the back of the machine, it's actually different air by the time it gets there. It starts off cooler, it ends up hotter. And as we go to cold plates, as we start to take away some
Yeah.
of the need for directly cooling some of the high value GPUs sitting at the front of the rack, they're actually
Yeah.
pulling out fans. They're reducing the number of fans in the system. So the problem is actually getting worse at the
Oh, so you
back of the
still have it.
box.
That's I was going to ask that
Yeah,
about,
yeah,
next generation racks, say the Kyber rack. Do
yeah.
you still have that
Oh,
problem of
I
the,
yeah. Every time I
okay.
read some knuckleheads press release around, we're not going to need fans anymore in a server. I'm like, sure you're not. Like,
Mhm.
show me exactly how you're going to get any kind of liquid cooling on a bank of DIMMs. Just show me, right? It doesn't.
Yeah.
It becomes again a geometry and a physics problem. You can't get cooling back there the way that you think you should. And oh, by the way, you really don't want a pipe going into your NIC card because your NIC card is replaced at a faster rate than the overall server is. So what am I going to do? I'm going to send the technician in and go pull a NIC card out and, unscrew tubing, and no, none of that's going to happen, right?
Okay. So you want something that's easily
Yeah, you just
accessible.
what you really want at the back of the server is, for lack of a better term, fire and forget. You turn on some air movement and you just go forward with it.
In these sort of next generation racks, the higher power ones, are you still using a large percent of the power budget, 15%, as you stated earlier, to cooling, to fans in particular?
No. We are not. I wouldn't claim that in terms of power efficiency, we're necessarily any better than an individual blower that might be in your laptop, for example.
Yeah.
We are going to be fundamentally more energy efficient in a server by virtue of the fact that we are actually close to the source of the heat, right? If you're relying on bulk air movement from the front of the rack all the way to the back, you actually have to get quite a bit of pressure and float in order to get back there, and that's where the inefficiency gap starts.
Gotcha. Okay. Thank you. So, and you did say that the technology was similar with laptops. I did look at the zoned cooling concept.
Mhm.
There was a white paper on this
Yep.
that Ventiva recommends, separating the heat exchanger or the cooling path that pulls heat from the processor from the skins cooling, and that
Yep.
is skins cooling is what manages temperature, the physical chassis that users touch. So that's
Yep.
like the keyboard.
Yep.
So you apply similar concepts to the server cooling architecture?
Yeah, I think it's counterintuitive, but I'll highlight it. The heat density problem in a laptop is actually worse than it is in a server. Two reasons. One is the size. You don't have as much physical space to spread out the heat in a laptop. Two, the constraints on that size also make air movement through these types of devices, laptops, really, really difficult. So in a laptop, what the solution we came up with, again, because of the geometric reality that we live in, is you can pull those generally. If you imagine where your keyboard is sitting on your laptop right now, right?
Yeah.
So generally over by the shift key and the return key, if you look at on the right side and the left side of your keyboard, there are going to be two fans in high end, right? Those are going to be two blowers that are taking up, generally, when we get right down to it, about 45% of the overall surface area of the motherboard, just for the blowers, right?
Yeah.
Nobody thinks about like the sheer amount of space for that. So what did we do? Because we know we've got air movement that we can fit in weird spaces, we get rid of those blowers and we move our devices, our ICE modules, all the way to the top of the board, underneath where the hinge for the screen is. That's normally considered kind of dead area. That frees up all of the extra space on the motherboard for doing anything that you want to, like maybe putting in SSDs, removable SSDs, or memory close to the processor if you're doing local language model or large language model inference in the machine. Those kinds of things, right? That's only possible because we can get good air movement coming through the system in the way that we architect the overall system. We design the system to use our stuff, basically.
Okay. Well, I understand that dust is a problem with all electronics, and ionizing air will generate ozone, right? So would you mind describing how Ventiva's ICE9 thermal management system, I believe that's what it's called, helps mitigate dust ingress in servers and ozone generation?
Okay, so in general, just we just call it ICE or the Ventiva cooling solution or something like that, right? We have different model numbers, but I don't want to confuse the overall conversation, right? So a couple things. Yes, dust is a reality in all of these systems. You got to remember on our side, though, that for us, we are a completely digital air mover. Like when you turn us on, air flows. When you turn us off, it stops immediately.
Yeah.
So it's digitally controlled, and in order to get the lifetime we need out of these things to run in these types of applications, in multi-year lifetime, We spend a lot of time monitoring how air is flowing through the device. It's fully digital, right? So we can tell you down to almost to the individual particle of dust, how much dust your system is ingesting. And we use that information, right? And
Yeah.
we actually can pass that information back on. And we're working with some laptop guys on this right now, where we can pass that information over to the laptop companies.
Okay.
How we handle that, though, how we monitor is we adjust the performance of the device based on the characteristics that it is operating in: high humidity, low humidity. If you're in Arizona versus Mobile, Alabama, you get two
Yeah.
different types of air, two different qualities of air.
Yeah.
Dust could, maybe you're in at somebody's house and they've got cats or something like that, and there's cat dander. We we can send we I can't tell you it's cat dander, but I can tell you there is absolutely something going on with the device, and we adjust accordingly. So that's one way that we handle life, and so far we're passing everybody's quality tests with that. The second question you asked is about ozone.
Yeah.
So back to the original physics, right? So when we're stripping this ion out of the air, you end up with, what they call monotonic oxygen, O1, which is
Yeah.
ozone, right?
Yeah.
And so we have a way of dealing with this. I think some people have said we've invented this. We didn't invent it. We're just using the technology in a certain way.
Yeah.
Again, high school physics. If you pass ozone or any type of thing like this over a catalyst, catalytic in your car, you have a catalytic converter,
Yeah.
right? The catalytic converter there is in there literally to convert the ozone back into oxygen, to give it an extra ion. So you get, instead of O1, you get O2.
Mhm.
So what we've done is we've created a manufacturing process whereby in servers or in your laptop, most air is blowing out of through or passes through fin stacks in order to transfer the heat to some other surface.
And
We
that's
coat
the yeah.
Yes,
That's
we
the
coat those.
catalytic converter.
Yeah, we coat those fin stacks with a catalyst.
Mhm.
And as the ozonated air passes over that, it grabs the extra the extra ion. It grabs the ion, and now you got O2, and it converts it out the back. And we tested this with all the different testing regimes. We passed just fine. Now the challenge, though, was figuring out a manufacturing process to take care of all that.
Okay. Okay. Do you mind talking about that a little bit more, the manufacturing process for that?
Yeah, it was painful. Because we're taking a lot of different industry knowledge from different sources, and we're applying it in a novel way in things like laptops. So I can't get into a lot of the details. We did protect
I
some of this
imagine it's
around trade secrets, but
proprietary.
we
Yeah.
have ways of coating the fin stack with a specific material and adherence and blah 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 blah. And then of course that all has to pass various quality tests out the other side. But we've worked our way through that. So it really did become a supply chain thing for us.
Okay. Okay. Um, this is kind of a side question, because
Hmm.
you are tracking, as you said, it's a digitally controlled air mover, and
Hmm.
you are tracking things like humidity and dust. And
Hmm.
does that tie into, predictive maintenance,
Yeah, there you
opportunities
go.
in
Well
data
done.
centers?
Yes, that's
Okay.
exactly right. So like
Yeah.
we can, and this is, I alluded to the fact that we're working with some of the computer folks
Mhm.
on this, is we can say, because we're monitoring it, it's essentially free information. We can pass that information back to, say, the OS in your system, and it
Mhm.
could say, you seem to be in a dusty environment. Do you want to throttle back your computer so you're not ingesting as much? You could do something
Mhm.
like that. Or if you're an IT department, you could be getting a bunch of reports, and everybody over in building, somebody brought a cat into building B. I'm making this up, right? But there's something going on over in that facility whereby we can do some preventative maintenance and get that all taken care of. And so that's a first for this stuff.
Mhm.
The single biggest point of failure in most laptops is this mechanical, bearing and grease thing we call a fan, dying and needing to be replaced. And our goal, part of our goal, is to just eliminate that need completely.
Yeah. And this was just a layout thing I remember seeing in a
Mhm.
video. You have one power supply and it can tie to multiple
Yep, exactly right. Yep.
ionic cooling devices. Okay, okay.
Yeah, exactly right.
Um, how are the data center validation efforts going now? Are you in co-development with any specific OEMs?
Yeah, I can't tell you who, but
I
yes.
know. Yeah.
I would say we're past the initial investigation stage, and we're working on
Mhm.
implementations with various and sundry folks. It's interesting. There's both folks that are building the racks themselves, and then there are the folks that are supplying into those racks. I'm thinking, like
Mhm.
Nick Card folks, those
Yeah.
kinds of things that we can
Okay.
work with as kind of on an aftermarket basis and go into servers as well.
That's very interesting. I one question. If
Mhm.
say it might be my last question. If ionic cooling becomes a standard technology in AI server design, what does that enable that isn't possible today?
Yeah, so the only thing I'd change about your question is when
Yeah.
it becomes a standard
Okay.
in.
Let me cross
Hey,
that out.
no, it's all right. I gotta get my mantra in there somewhere. So when it becomes a standard, what are the things that the essence of your question is what makes it different in those
Yeah.
instances, right? Okay, so I, we are, I kind of, I would say our first emphasis in this stuff has been laptops. That's really where a lot of the traction has originally started. It's since moved on into other adjacent applications like the data center. But if I just stick with the laptop for a second, we have a vision that says in the next 2 to 3 years, the laptop that you're working with, there's a certain you and I would qualify in this category. We're knowledge
Yeah.
workers. We're people that are going to be interacting with some form of machine learning or large language model on our laptops, and we believe there's an opportunity coming where a lot of that inference, the workload is changing to inference, is actually going to be happening locally for you and I. There's certain things we do not want to be sharing up into the cloud, things like
Yeah.
that.
Mhm.
Okay, that has a whole host of implications. Two big ones being, in order to run local inference on your machine, you need a lot of memory bandwidth. It's a memory bandwidth problem, not necessarily a compute problem. And to satisfy memory bandwidth, you better have a lot of local memories close to the processor. And if you're
Mhm.
going to do that, you need the space. Like
Okay.
putting fans in a laptop precludes being able to do local inference, period,
Mhm.
full stop, right? So the very first thing is we will enable a class of machines that heretofore could not do as much really world-class language models running on your machine. That's the first thing. The second thing is if you've ever run a machine that could a laptop that could really do a lot of local inference, they are loud. The folks that can do this, my good friends over in Cupertino, if you fire up a laptop running I don't know, a 122B model on
Yeah.
your M5 Max laptop, that thing sounds like a jet engine after a while. And
Yeah.
that's not a really good experience for the user. We get rid of that entire problem. We're completely silent, no noise, no vibration, and we've opened up the space, right? So the difference we believe you're going to see over the next 2 years is if you're going to do local inference on the machine, you're going to find that Ventiva is the one that made it happen.
That does expand the application space quite a lot. Local inference, we're talking, edge compute or,
Exactly. Yep.
potentially robotics as well,
Yep. You got it exactly right. Yes.
automotive. Okay. Okay.
Perfect. I was just at Embedded
Okay.
World in Nuremberg talking about this exact same thing. If you're going to run local inference and you have to, by definition, embedded is real time. You're not going to go out to the
Mhm.
cloud
Yeah.
every 2 to 3 seconds. You better have an answer for memory bandwidth. And if you have an answer for memory bandwidth, then you don't have a fan.
Mm. You need the space.
You need the
That's
space. It's a geometry thing, which is just what we were talking about at the very beginning.
yeah. Um, is the cooling technology constrained to the sort of rectangular shape, or can you do sort of more free form? This
Yeah, you did great.
is
No, no,
that
no. I love
okay?
this question,
This
right?
is
So go back to the
yeah,
Lego analogy, right? So
yeah,
Legos are all rectangles, but
yeah,
you can build all these crazy shapes by linking them and turning them at angles and things like that, right? You can
yeah.
stack them on top of each other. If we
Gotcha.
give you the building blocks, you can create all these alternative shapes, and that's what we
Yeah.
try to do. right? So we give you varying lengths of our device, and then you can mix and match those in order to get to the shape and performance that you need for your particular application.
Gotcha. Thank you. I don't think I have any more questions, and I they'll probably come after the interview. But do
You
you
can
have?
just call me anytime you want.
Thank you.
You can tell I love talking about this stuff, so I'm happy to.
Well, do you happen to have any kind of final comments? Anything that I might have missed?
I don't know. I don't think so. You got to you generally, I will tell you, most people don't really carry it forward into like, could you do the alternative shapes thing? So that would
Okay.
be the area I would normally encourage you to think about, but you already went
Yeah.
there. So.
Okay. Okay. Well, thank you so much. I've really appreciated this conversation, Carl.
Oh, me too. Loved
It's
it.
been great. You know, it'll be really exciting to see how Ventiva moves into these different application spaces. And I know we've been talking data center, but even beyond that as well. So I really
Awesome.
appreciate it.
Thank you. Thank you for your time.
Thank you.